Good afternoon, dear student, and welcome to the sixth edition of our function analysis class. I hope you have been going through the other videos, reading the notes, and I hope so far so good. So today I'm going to go through the slide that I uploaded last time. We haven't had the chance to go through the notes together. So that's what I will try to do and also explain the important concepts. Okay, so last time when we parted, we discussed about outer measures. And I gave some example of outer measures. And I think I only mentioned these two examples. Okay, so today we are going to continue with examples, particularly the third one, which is called the Lebesgue outer measure. As you can see, Lebesgue, when you write Lebesgue, there's S there, but that S is not pronounced like in castle. You see, when you pronounce castle, you pronounce castle, but when you write it, there's an S. That's not right? Cast, there's an S, but that one is not pronounced. It's castle. So it's Lebesgue, G like tongue. When you say tongue, don't say tongue. No, you say tongue. It's the same thing, Lebesgue. Okay, so Lebesgue outer measure is defined this way. So maybe to represent that, maybe the best way to see. Let's say, for instance, in the case of, okay, you see we are using PR, the power set of R, and this set A is a subset of R. It can be any arbitrary subset, right? Obviously, if A is an interval, obviously the cover, of course, it will depend whether A is an open or closed interval or semi-interval. That is, when you say semi-interval means that it can be open on one end and closed on the other, and vice versa. Okay, so if A is an interval, if it's an interval, now the cover that you'll be taking here will be the smallest open interval that contains that interval. If A is an open interval, then the coverage, this one, the cover here, will just be that single interval, which is A itself, if it's an open interval. And in that case, the summation, since there's only one, it will be that interval, and then you take the length. Then if you take the inf, it will be exactly that one. So in that case, mu star will coincide with the length of that particular open interval, which in this case will be A itself, in case AE is an open interval. If it is closed, you take the smallest open interval that contains that one. And then you will take the inf of that. That is, when you take the inf, it will be the smallest, right? It will be the smallest. And the measure, the outer measure of A will be the length of that interval. Okay. Now, if A is the union of interval or union of particular type of interval, because it's an arbitrary, so it's a subset, it can be of any shape, it can be of any form. Now, let's assume that A is something like this. If A is, maybe here you have an interval, maybe close here. For close, I will put the dot to say it's closed. I will do this to show that it's open. So that is it. Maybe you have another one, maybe close, open. And here there's a gap, right? It can be closer, there can be a long gap. It's still a subset. And now the next one, we can take close here, close there. And it can be, let's say, finite. If it's finite, it's the union of this finite interval. So your OI, this will be like O1. O1 will be, you can take this one, and you take something. It can be this. It could be an interval that contains this point but open there. So we could take something that is here like that. And with this actual opening, this one. Yeah. Or you can take it a bit larger. Similarly here, you could take this open interval that will include this one, that will contain this dot. And you can take the boundary of this dot, of this, you can take that, the border of that. And here, the same thing, you can take the smallest open interval that contains that one. And then this will be your O1, this will be your O2, and this will be your O3, right? So you take the length of each and then sum them up. Right? And that is it. And that will be your mu star of A. Right? Because that will be the smallest, right? Because you try to take the smallest. Because this inf, in fact, is on the A, on the O, on the open set. So this summation, this inf is on the open set. Yeah, this open interval. Because there could be many. There could be many because you can say that this is a covering of A. There are infinitely many covers. So among the covers you will take, the one that will give you the smallest summation. So when you compute the summation for a particular covering, compute the summation for a different covering. So you compute the summation for all possible coverings of A, and among these sums, you take the smallest possible, the infimum of all these summations. So the summation, the infimum, in fact, will be on the covering. Okay, so that's roughly to give you an idea of what the definition is all about. All right. And now from this outer measure, we are going to define the Lebesgue measure using this theorem, which is like the Carathéodory extension theorem, because with the Carathéodory extension theorem, this mu, the extra information that we can add for this to be, for this mu to be the Carathéodory extension is that this mu is complete. A complete measure means that for any, okay, I did not mention that definition here. But a measure will be said to be complete. Sorry, when any subset of a null set is measurable. That is, if this is satisfied, so mu complete, that is complete measure, if any if for any, let's say E subset of A such that mu A is 0. So mu A is 0 means that A is what? It's a negligible or it's a null set, right? So here, this means that A is a null set. So any subset of a null set is measurable. Mu measurable. So if this is true, we say that mu is complete, and that's the case for the Lebesgue measure. Any subset of a null set for the external, outer Lebesgue outer measure is measurable, right? So any subset of a null set for the outer for the Lebesgue outer measure is measurable, right? And also because it's a subset, it is also a null set because we know by the monotonicity of mu that if E is a subset of that, mu E will be less than or equal to mu A. And we know that mu A is 0 and a measure is positive. So mu A also is a null set. Right. Okay, so this is the definition of a complete measure. So I define it because the Carathéodory extension theorem is because I mentioned the Carathéodory extension theorem. So in the Carathéodory extension theorem, you have the above and this extra information. The extra information that the measure is complete, right? This measure mu is complete. So if we add that, this proposition will become the Carathéodory extension theorem. Okay, so if you apply this proposition to the Lebesgue outer measure, so the restriction of the Lebesgue outer measure to M mu star, that is the set of measurable or mu star measurable set, we obtain what we call the Lebesgue measure. And so we are here. Okay, obviously, as noted here, you can see instead of mu, but for the Lebesgue, we can call it lambda star, and the Lebesgue measure will be called denoted by lambda. Okay, so that's the connection between Lebesgue outer measure and Lebesgue measure. So the Lebesgue measure is just the restriction of the Lebesgue outer measure to the sigma algebra of Lebesgue measurable sets. And that one, we give it a particular name instead of calling, instead of denoting as we did here by M lambda star, we'll just call it calligraphic L this way, LR or just L. So in textbooks or in the literature, that's how you see. And L stands for Lebesgue because Lebesgue is Lebesgue is when you write Lebesgue, the first letter is L. That's just to refer to the Lebesgue. Okay. Another useful information is the connection between the Lebesgue sigma algebra and Borel sets. Lebesgue is larger, so the Borel sigma algebra is contained in the Lebesgue sigma algebra, as you can see here. Lebesgue sigma algebra is the union of the Borel sigma algebra and the set of null sets. The set of null sets. So it's the union of the two. And another property of the Lebesgue measure, which we define here, obviously it satisfies all the properties of the measure, but another important property is that it is invariant under translation or by translation. So this is what it means. If I have a set, I want to compute the Lebesgue measure of that set. If I translate it by any quantity, the measure will be the same. It's as if I have a... Okay, so if you see this is my... This is an external hard drive. You can see that the measure, if I measure the volume of this, okay, this is in R3 now. This is R3. You can see that even if I move it, I translate by a vector in any direction, the measure will be the same, right? It will not change it. Okay, now if I assume I am in R2 is the same, you see this ruler, if I translate and I measure the area, because that would be my measure in R2. In R3 is a volume, R2 is area, in R1 is a length, right, of the interval. Now, if I look at this length in R1, you see that even if I move that ruler, move it again, but the length is still the same, right? That's exactly what what this means. If I translate a set or Lebesgue set like this one, if I compute the measure of the translated set and the original set, the two values will coincide. Okay, this is how we define A plus B, right? For A, an element of the Lebesgue sigma algebra, because this is a set, right? And this is a number, a real number. So by definition, it will be A plus B, where A is any element in A. Okay, now the next thing that we are going to look at is an overview of the Lebesgue integral. We will not go into all the detail with the theorems, the lemmas, but here we are just giving the results, right? It's an overview of the results. Because as I mentioned in one of the videos, Lebesgue measure or integration theory is a semester class, it's a semester module. So in a few hours, we cannot cover everything, but what I'm delivering here through the slide is just what you need to know to tackle problems related to this. Okay, in order to define the Lebesgue integral, we need, first of all, to motivate why we need Lebesgue integral. It's just simple. It's because it was noticed by my colleague Dan that there are functions that are not Lebesgue integrable. Sorry, that are not Riemann, sorry. that are not Riemann integrable, but which integral exists in the Lebesgue sense. Such a function is the Dirichlet function, as you can see here. The Dirichlet function is defined by this quantity. So the Dirichlet function is defined on the interval, the closed interval 0, 1, and it takes the value 1 on rational numbers and 0 on irrational numbers of that interval. And the simplest way to denote it is the indicator function of Q intersection the closed interval 0, 1. Q being the set of rational numbers. So the Riemann integral of this does not exist. As you know, with the Riemann integral, for the Riemann integral, we define two quantities. We define the lower integral and the upper integral. The lower integral will be the minimum, so we take the minimum, we take a partition of the interval, and in each subinterval we take the lower value, and we sum them up. It gives us the lower, right? The lower sum, or the lower Riemann sum. And now the other one, the upper Riemann sum, in each subinterval of the partition, we take the maximum value, sum them up. So it gives the upper Riemann sum. Now we just take the limit of both. If they coincide, right, we say that it is Riemann integrable. And the common value of the two limits is what we call the Riemann integral of the function. Now, if you look at this function, the way it is defined, regardless of the partition that we take of the interval 0, 1, regardless of the partition in any by density of Q, in any of those subintervals, by the definition of this, you have 0 and 1, right? 0 and 1, because there are infinitely many rational numbers, and in between those rational numbers, you have irrational numbers, those that are not. So there will be 0 and 1 in that partition, that partition, that subinterval of the partition. Now, if you look at the lower limit, it will always be 0, because the function here takes only two values, 0 and 1. So the lower will always be 0 for all the subintervals. So if we sum them up, we still get 0. The limit of 0 is 0. So our lower Riemann sum here, the limit of that will be 0. Similarly, for the upper, in each subinterval, you always have 1 because they are irrational, so they will always be irrational number. If you sum them up, right? If you take the sum in each, you have 1. So if you sum them up, you have a finite number that's not 0, right? That's not 0. So you see that the limit will be finite, and the other one, the limit is 0. So you see already that the lower Riemann sum and the upper Riemann sum are completely different. So they cannot give you the same value. So we can conclude with this that the Riemann integral does not exist because the lower, the upper integral, the lower integral and the upper integral will not give you the same value. But we will see that for this same function, the Lebesgue integral exists. So that was the motivation. That was the motivation for the Lebesgue integral theory. Okay, now we're going to recall what is a measurable function. We know for a function defined from x and though with a sigma algebra A and to y, that is f is different from x to y, where x is endowed with a sigma algebra A and y is endowed with a sigma algebra f. So f is said to be measurable if for any measurable set B in F that is in the range, the preimage of B is a measurable set, element of A, that is A measurable. So this is important to recall. Now, indicator function, I mentioned it already here, the indicator function. So the indicator function of a set A, non-empty set, given by this definition. So it indicates whether an element is in A or not. That is, for X, indicator function or one AX is equal to 1 if X is an element of A and 0 otherwise. So we have this result. A is measurable if and only if its indicator function is measurable. And you can prove it. I encourage you to do the proof yourself. This one. And why do we need this indicator function? Because they are the building blocks to define a Lebesgue integral, right? Why? Because as you can see, look at this one. From the Riemann integration theory, Riemann integral, for this function, for this indicator function, you can already find the integral, right? What will be the integral of this? It will be the length of that, because we Riemann, you say it's the area below the curve, right? So this area, what is it? It will be the length of this, or the volume of the, in fact, we call it the measure, because we might be in 1 dimension or 3 dimension or whatsoever. So regardless of the dimension in which A lies in, the dimension of the space in which A lies in, because this A can be a volume, it can be anything. So you measure this, so that will be the measure of A times this height, which is 1. So that integral is just the measure of A. So now, from this indicator function, we can define what we call simple functions. A simple function will be what? It's a function that takes a finite number of values. That is A1, A2, A3, up to AN. So a function that takes a finite number of values is called a simple function. But we can express a simple function in terms of indicator function. You can write it as a linear combination of indicator function. Now, how are we going to select the sets? Because when you say indicator function, it is indicator function of a set. Now, the set that we are going to use in this case will be the set that will contain, when we say f takes a certain number of value, so the range or the preimage of this value will be our set. To make it simple, let's say, for instance, I have a function that takes the value 1, for instance, like this. Now, what is the preimage of 1? For this case, it's A. Okay, let's say that our simple function takes 3 values, A1, A2, A3. Now, how will I get the the indicator function. So for A1, I compute the pre-image of A1. Right. If f is a measurable, in fact, indicate a simple function is a measurable function. Now this one will be a measurable set, right? This one will be a certain A1. So if f is measurable, A1 is also measurable. And this A1, the pre-image of A lowercase a1, that is what we will take to be our A. And then for that particular, for others, so I can just say A sub I, where I run from 1, 2 to 3. So this is how we will compute our A1. And finally, what will be our f? It will just be the sum of all these indicator functions. Oh, sorry. It will be a sub I, indicator function of ai. 1 to 3. You see? And by so doing, all these AIs will be disjoint. They will be disjoint because the pre-image of A1 will not intersect with the pre-image of A2. Because if they intersect, it will mean that f will take two different values on the intersection, which is not the case. Right? It cannot take two different values. Okay, so this is how we will construct our simple function of indicator function. Great. Okay, so this is how we define then the indicator function. Now, if we want to compute the integral, as I already mentioned here on top, that the integral of an indicator function will just be the measure, right? The measure of that. Now, for a simple function, this is a simple function, as I already defined. Now, if we integrate this, we know that integral is linear. Of course, we are still defining the integral. But we can show that the integral, defined this way, is linear. So if we take this, the integral of f, it will be sum of ai integral of this, which will give you directly the measure. Anyway, you don't need to do that. The best way to look at it is just to represent the simple function graphically, as you can see here. So this space, this is a real value function, that is, the value is in R. But here, this x can be R1, it can be R, it can be R squared, it can be R cubed, it can be Rn. So meaning that when we call the A here, it can be in R, it can be R2, whatever, right? So this will be the space in which it lies. So this line does not necessarily mean that it's a straight, I mean, we are on the number line or the real line. It can be R2. So this can be a plane, it can be the space. Okay, so now we know already that since this is a simple function, it takes a finite number of values that we denote by a1 up to an. But here in the representation, we only use 5 values, right, for illustration purposes. So this is our a1, a2, a3, a4, a5, a6, a7, right? Depending on the various value that this will take. Right? So on a1, it takes the value lowercase a1. On a2, lowercase a2, and so forth. Now, the integral of our simple function will be the area under this, right? So what is this area? It will be, if we are in the plane, it will be the area times the height. That would be a volume, right? In this case. So you take the length or the measure, the volume, it's good to call it measure. So we take the measure of A1, of A3 in this case, the shaded part here. So we take this will be the measure of A3 times the height, which is A4. So if you multiply A4 by the measure of A3, it will give you this full area. It can be a volume, it can be what, but it's a volume. So this is what you have. So we can do the same for each sub-interval here. Let's see sub-interval, let's see if it's R1. And then we sum all this up. Okay, you can see that in between, here, the value is 0, right? In between there is 0. Right? The function takes the value 0 in between. Right? Obviously, if you take the value 0, we don't include 0 because it does not contribute into our integral. So our A case here are the non-zero values. Right? Okay, now if you sum all these, it will give us that. So that is the integral. It will be the sum of this. So by definition, that's our integral. So we can use that definition to show that this is linear. All right. Now for an arbitrarily measurable set A, we can define the integral. We can define the integral of this measurable, this simple function. Because remember that for this simple function, this integral is on x, right? It's on x. And give this. Now, if we take, you want to measure it on a particular measurable set A. That set A can be anything. It can be, I can take a set like this. That start maybe from A4 up to A7. Or you can even go above it. But it only takes a finite number of values. So what we will need to do, we need to take the intersection of that A with this A case. So that's what we get here, right? Because we're integrating on that. So if we integrate on A, we need to take only the portions of A that intersect with the A case. Because F has a finite number of values. So we take the intersection so as to consider only the values of A that lies on at the intersection of A with the A case. So that's how we define the integral of a simple function along an arbitrary or over an arbitrary set. Now, what if we have a measurable function, which is not a simple function? There is a result that I did not state here, but the only thing we can do here is first of all to define the upper and the lower integral of f. And those will be defined in terms of simple functions. So that's what I said in the beginning, that indicator functions will be the building block, right? Or simple functions, because simple functions are based on indicator functions. So in all the theory, we will be using simple functions to approximate measurable functions, right? It's exactly the same thing that we do in Riemann integral. Remember that when you want to integrate a function using Riemann integral, take that function, it can be a continuous function or a bounded function, and then you approximate that function using using constant function. piecewise constant function. Take the function, you approximate it with piecewise constant function. That is, you take a partition, and in each subinterval of the partition, you approximate it by a constant function. Or you take the lower value of the function on that interval, it will give you the lower limit or the lower Riemann sum, and you can also take maybe the maximum value of the function there. So actually, you approximate it with a constant function. Constant function. That is exactly the same procedure here. We have a measurable function. We approximate it with constant function, which are measurable. I mean, which are what we call simple function here. So for the upper integral, sorry, is it upper? Okay, upper integral, yes. For upper integral, you see that we will approximate this function f with simple functions that are greater than or equal to that function, as you can see here. And then we compute their integrals, and we take the infimum of all of them, the infimum. Okay, maybe if I want to represent it graphically, this is a situation, for instance. Let's say the function is something like this. Let's say this is our measurable function. The function is like that. Okay, with the Lebesgue, what we usually do, we don't partition the interval. I don't know if you are in R. Let's say that here this is R. We don't do like, we don't proceed as we do with the Riemann integral, where if you integrate from A to B, you take that interval AB and then you partition. No, we don't do that. We don't partition. But what we do, what you partition instead is the range of the function. So the function takes value from here up to there. So let's assume that this is our y-axis, just a real value function. So if you assume that this is our y-axis, and then here this is our interval AB. Right? If you assume that it's a function from R to R. So with Lebesgue, you look at this first. You look at the value, the range. So you look at the range. So you have something like this. And then you have that. So this is the range. So actually, what you partition is the range, not the domain of the function or the interval AB. So this is what you partition. You partition this. You partition this. And then you look at the pre-image. The pre-image of these values that the function will take will give you the A's. These A's, A sub K's. That's how we get, we don't chop this into sub-interval. We don't partition A and then look at the, no. We start with the value taken by the function, and that's why we partition. And then we look at the, okay, now, since we said that we approximate this function for the upper integral, so what we do, we look at simple functions that are greater than or equal. So here, I can decide to approximate it with a certain number. Let's say that the first is this one. We'll take this value. Another one, I can take this one. And the other one, I can take that. So for instance, I can decide to approximate this with a simple function that takes only 3 values, right? Now, if that is the case, so I will take these 3 values. So I will take this value, and finally that other value somewhere here. So that will be my simple function. Right. Now, I will take, so the pre-image of this point, let's say 1 point, 2 point, 3 point. So this is A1, A2, and the other one is A3. They are so close that A3. Now you can see that the pre-image of this A1, there will be this point. But since it continues, there's another point here. That will still give me that value. Give me this one. This one and that one, for instance. Right. Obviously, this is for the real line. So for the real line, it will give me 2 singleton. And those singleton are what I will use to define my A1 and A2. And I will compute the measure of that. Right. Okay, if it's not a singleton, it can be a subset of that interval. And that's how I will construct my simple function. So that's how I construct my simple function. So it could be a sub-interval depending on how I select my partition here. This value. Or I can take a range. No, not a range, because we are dealing with a simple function. So since we are using simple function, so it takes a final number value, then we take the range, so the pre-image of these values, and then it will give us the sub-intervals that we'll be using here. Then we measure them, we take their measure, we multiply by the A's and sum them up. Therefore, it will give us that integral, this integral. So we do that for all possible simple function that is greater than or equal to A. And we take the minimum of all those. That will give us the upper integral. Right? So for the lower integral, we do the same thing. We do the same thing. Good. So it's the same thing that we will do for the lower limit. We take the supremum. Obviously, in practical application, you can see that it will be difficult to use this one. This is just for, it's mainly used in the proof, right? This type of definition is mainly for proof. But in application, you don't use it this way. You take, there's another theorem that allows you to take, in fact, there's a theorem that states that if a function is measurable, like in this case, it can be approximated by simple function, right? Increasing simple function. It can be increasing if the function is, if you take a bounded function, you can always take an increasing sequence, right? From below, right? That will converge towards the function. And then you approximate that integral by the limit of the integral of this increasing function, this sequence, an increasing sequence of simple function that converges to this measurable function. So you approximate the integral by that the integral of those, instead of using the supremum or the infimum. They are just good for proofs, to prove theorems and the like. But in practical application, you just take a sequence that converges, a sequence of simple functions that converges towards f, and then compute the limit. You compute the integral of each one, and you go to the limit. That limit will be the limit of your function. Okay, so it's worth mentioning this. Okay, now the Lebesgue integral of this measurable function would just be In fact, the function will be Lebesgue integrable if the upper and lower integral are equal and if they are both finite, right? So that's what I indicated here. If they coincide and they are finite, we say that if the function f, the measurable function f, is Lebesgue integrable. And its integral will be this common value taken by the upper and lower integral. And now the set of Lebesgue integrable function is denoted by L1. L1. So there's a difference between this L, because we remember for the Lebesgue integral, to indicate that the function is Lebesgue integrable, you use this calligraph. But for the Lebesgue, you remember the other one? The Lebesgue sigma algebra is this one, it's denoted this way. Whereas for Lebesgue integrable, it's L like this. The L1 is just to indicate that it's the function itself that is integrable. If it's square integrable like this, so if absolute value of f square is Lebesgue integrable, we will denote it by f is an element of L2 to indicate that f is square integrable, right? That is, the square of f is integrable, is in L1. So, but if the function is p integrable, I mean, if the fifth power of f is Lebesgue integrable, right? We denote it by f is an element of LP. Of course, this LP is different from capital LP, like that. They are different, right? This is cursive or calligraphic LP. So this notation are important. So they're important to distinguish between them. All right. So in general, when we talk about these L spaces, when we say L is an element of that, this L denoted L1, in fact, it's a short form of L X A mu, where X is the set, is a set, and A is a sigma algebra over X, and mu is a measure defined on A. So this is our measure space, right? So we will integrate over a measure space. But because this is long to write, we can just denote it by L like this, or still we can also denote it by L1 of X like this, of X. L1 of X. It's the same thing. It can also be different. But in general, you will not see the A's and U. If they are not explicitly indicated, know that this X is a measure space. Measure space. It has a sigma algebra and a measure. Okay. Because you integrate with respect to a measure. I think maybe I didn't, I wrote it surely, but I did not, since we start, oh, okay, it's here. It is here. I forgot to stress on this. When we say Lebesgue integrable, it is with respect to a measure, right? And that measure is the one that I indicated here by me. That measure is not necessarily the Lebesgue measure. When we talk about Lebesgue measure, that will be in a particular setting. So this definition is a broad definition of Lebesgue integral. It is defined, that integral is defined with respect to mu, an arbitrary measure, right? It's an arbitrary measure on the set X, or on the sigma, or one of the sigma algebra. So it is not the Lebesgue measure that we are using here. That means the mu we are dealing with here is an arbitrary measure, not necessarily the Lebesgue measure. So this precision is worth mentioning, right? Okay. In the previous slides, the function f we were integrating, like in this case when we talk about measurable function, you can see that the function takes its value in r plus bar, which is called the extended positive real line. Right? This is a positive real line from 0 to infinity. Excluded, but now we extend it to include infinity. So that's this when you see the bar is the extended real line. The bar is for extended real line. But these are extended positive real numbers, right? So we are dealing with positive functions or positive measurable functions. So everything that was done with positive. Now, if the function is not positive, meaning that it's it is of an arbitrary sign, it takes positive value in some area and negative values in other area. So we can always define that function f as the difference of two positive functions, and to each of these positive functions, which are measurable, we just apply this because they are positive, right? So f plus and f minus are positive. So you approximate them using the above theory. And now to get the integral of the function f itself, you just combine the two. Yeah. So f plus and f minus are given by this. They are positive, right? The max between 0 and f, if f is negative, the max will be 0. But if it is positive, f plus will be positive. Similarly here, f minus is the max between 0 and negative f. So if f itself is negative, its negate will be positive, and will always give you that part. And absolute value of f will just be the sum of the positive part and the negative part of f. Now, f will be Lebesgue integrable if and only if the positive and the negative part are Lebesgue integrable. And its integral, which I did not mention here, its integral will just be the sum of the integral of the positive or the difference, right, with the integral of the negative part d mu with respect to mu. So that's how you write the integral of an arbitrary function, or a function of an arbitrary sign, which is represented as a difference of its positive and its negative part. So that's how you integrate. That's how you write this integral. Okay, the last part I need to cover before we part is the convergence theorem. I mentioned the convergence theorem, but I did not state them. All right. Okay, I think I already covered this about the LP spaces. I indicated that already. All right, so these convergence theorems, as I mentioned, there are 3 types of convergence theorem. And there are many, but the fundamental that anybody should know or must know, it's even good to say must know, are these 3: the monotone convergence theorem, which is also called the Bepo-Levy. In some textbooks, they are called Bepo-Levy. You see, Bepo-Levy is the same as monotone convergence theorem. Okay? Maybe I should write it here on top, but most of the text will talk about that. But you might see also this Bepo-Levy. Bepo-Levy. I don't know that Levy, if it's Levy like, yeah, I think it should be with I instead of Y. The polarity is the same thing. You have the Fatou lemma and you have the dominated convergence theorem. These are the three fundamental theorems. As I already explained, they help to solve the problem of whether we can take the limit under the integral sign. Okay, so roughly speaking, we have a sequence of measurable function Fn. So Fn is a sequence of measurable function or sequence of integrable function. And we want to know when can we do this? Because you cannot always take the limit inside. It's not always true. You cannot always do that. So this will be true under some restrictions. And those restrictions are given by this theorem, those results, the convergence theorem. Okay, now let's look at the first result, the monotone convergence theorem. Okay, monotone convergence theorem just indicates that the function that, I mean, there's this sequence is an increasing sequence, right? So if you have a sequence, this one, okay, I'll call it monotone convergence theorem. Let me state it. Monotone convergence theorem. This is the first theorem. So this sequence is increasing. You take an increasing sequence. So Fn is increasing. You have an increasing sequence. It's increasing and it converges to the function f. So f is the limit of all this Fn. Of course, they are integrable because we cannot write that integral if the function f is not integrable. You cannot write integral of Fn if it's not integrable. So all the Fn are integrable functions. So from Fn integrable, integrable. Okay, now if this sequence converges to a function f increasingly, right? Monotone convergence. That's why we call it monotone convergence. It converges. It's not just a simple convergence, but it's a monotone convergence. So it increases and converges to f. The first result is that f, the limit, is also integrable. And we can pass the limit under the sign, the integral sign. So the result of this monotone convergence theorem is that f, the limit, is integrable and it gives you the value of the integral. So what is the integral of f of x d mu? What is this? It is exactly equal to the limit of this. So we know this. If we take the limit inside, we get that. See? Because we know all the Fn, we know the integral, because we know that it's a sequence, we have them. They're they are integrable, they converge, right? So these are known. Now, you can see, so you can see that this is equal to that. So we know this, so we start from this and we reach to that. So in other words, if I substitute this this because f is the limit. So if I write that this equality, you can see that we just took this limit inside, and we have that equality. So that is the monotone convergence theorem. So the restriction is that this sequence has to be an increasing sequence that converges towards f. Restriction is the monotonicity, the fact that it's an increasing sequence. So that's the restriction on the sequence. So monotone convergence is increasing sequence. So that's the restriction. Now the second one, Fatou lemma. Fatou lemma, oh, if you recall previously, a few videos, I'll be having a class. I'm just checking. I'll be having a class. Oh, yeah, in about 30 minutes. Yeah, about 30 minutes. There's a Fatou lemma that we stated, but that was for, it was Fatou lemma for measures, right? Fatou lemma for measure, where you use the limit inferior. And there was an inequality. I think I think I even promised to come back to this. Fatou lemma. Okay, this was the name. Fatou lemma for me. Okay, yeah. You have that information there. Okay, so this is the Fatou lemma. Okay, now the Fatou lemma, our Fatou lemma, you just replace this mu with the integral. You replace mu with the integral. So Fatou lemma will be the integral of that okay, Fatou lemma, I will call it FL. Okay, for Fatou lemma, there's no restriction. Okay, so I have a sequence of integrable function such that Fn converges to f when n goes to infinity. Now, what can I say about f? So Fatou lemma tells me that the best, because can we take the integral, the limit under the integral sign? It tells you that, okay, since there's no restriction, for any arbitrary, the best we expect is that the integral of the limit, that is this one, the integral of the limit, that is the integral of f, which I will replace here. In fact, it's limit inferior, because if it converges to f, the limit inferior and the limit superior coincide, right? We know that for a converging function. So the best then we can see here is that this will be less than or equal to the limit inferior of this integral that we know, this integral. The integral of this, they are integrable, so we know the integral Fn d mu. So this is the best we can say. Of course, when n goes to infinity, even though I didn't write it there. So the best we can say, we cannot say whether they will be equal, but this f is the limit of f, the limit will be less than or equal to limit inferior of this integral. That's the best we can say. We cannot say whether they are equal or not. No, we don't know that. So that's the Fatou lemma. So there's no restriction. So if you have a sequence of function like this that converges to f, you will always have this. But monotone convergence theorem and dominated convergence theorem are restrictions. So if you look further on the property of the Fn now, if there are further restrictions, then you can say whether there will be equality. But the best you can say for any sequence of any converging sequence is that the integral of the limit inferior of Fn is less than or equal to the limit inferior of the integral. Okay, so finally the last one is the dominated convergence theorem. That's the last result. Okay, dominated. What is dominated? So it means that dominated indicates inequality somewhere. So the statement here is that if we can find an integrable function, G integrable function, such that all the Fn are less than or equal to G almost everywhere. Meaning that the set of value for which this is not true is a null set. That is, mu of that set is 0. So almost everywhere, for almost all x except for x in a set whose measure is 0. Okay, obviously this G is positive, right? Otherwise, if G is not positive, you cannot write that. So this G is positive, right? Okay, so now we say dominated convergent theorem means that these F, these terms of the sequence are dominated by a measurable, by an integrable function. So the result of this is that the function f is integrable. Obviously, if you take the limit here, you will see that we're bounded by a function that is integrable. So it's integrable. So f is integrable. Instead of writing it's integrable, you say it's an element of L1. It's integrable. And you can take the limit under the limit of the Fn d mu when n goes to infinity will be equal, you see, now I can take it inside, will be equal to the integral of the same limit of Fn. But this is the function f itself, right? So this is integral of f dm. So we can take the limit inside. So if you take the limit inside, you get that equality. And this is f, the integral. So these are the measure theorems. Please, you can check in the prescribed textbook. You will see. Yeah, I didn't write specifically, but I explain, just for you to understand. Instead of, it's better to understand the meaning of each of the theorem. Right? So that's why I try to explain in a simpler form. Okay, I will stop here. You have everything. I hope you will enjoy this. If there's something you don't understand, please let me know so that I cover this again. Thank you so much for your kind attention and for your patience. God bless you and see you next time. But don't forget to remind me about the session that I suggested, if you can have a session over the weekend at your convenience, right? Thank you so much. Bye-bye.